Hello everyone. So today the lecture is for week number 5. So 1 month has passed. Time flies always, as you know. Okay, so in the last lecture we have overviewed the physical meaning of degenerated lead-up semiconductor as introduced in a slide. Right? So terminology N plus indicates a very heavily adopted N-type silicon material in which its Fermi energy level is very close to the conduction band edge E sub C. And similarly, P plus indicates a very heavily doped P-type silicon material in which its Fermi energy level is placed very closely to the valence band edge E sub V. So as I told you, the doping concentration to tell us N plus or simply N is 10 to the 8, 10 to the 18. So last top slide included in chapter 2 is band gap narrowing. So on the left hand side, you can see that the band gap energy variation and how much band gap energy is lowered, decreased because of the heavy doping concentration, such as the 10 to the 18, 19, and 20. So depending on the doping concentration, the delta E sub G, band gap narrowing, uh, can be increased. Okay? So as described here, once doping concentration is a significant fraction of silicon atomic density. So let's remember the value of the silicon atomic density. What was it? Yeah, 10 to the 5 times 10 to the 22 per cubic centimeter. So this indicates how dense the silicon atoms are placed within a silicon crystalline material. Okay, so if doping concentration is a significant fraction of it, then the energy band structure is perturbed. Perturbed means, simply speaking, changed and varied, okay, modified. So the band gap energy, so as we have learned, the band gap energy, EC minus EB, or Eg, is a kind of constant for a given material. However, the material is heavily doped with impurity dopant atoms, then its band gap energy can be perturbed, resulting in reduced band gap energy. So on the left hand side, you can see a plot showing how much band gap energy has been lowered as a function of a doping concentration. So with a higher doping concentration, the band gap energy lowering is increasing. So here is an analytical form how the band gap energy lowering is associated with the doping concentration as well as temperature. So for given room temperature, at room temperature, the band gap energy lowering is proportional to the doping concentration to the 1 over third, 1/3. Okay. Okay. So, well, this, I mean, the very simple understanding why band gap narrowing is happened is as follows. So as we have learned, the energy state indicating the donors or impurities, is placed and marked near to the conduction band edges. Okay, conduction band edge is what was the meaning of the x-axis? As I told you, uh, the location of atoms, right, across the silicon crystalline material. So the dopant atom is not continuously placed into the silicon crystalline material because it is a pure impurity. So here and there, the dopant atoms are randomly placed within a silicon crystalline material. So when drawing the NH band diagram, the notation to indicate the donor's atom in a silicon crystalline material should be dotted line instead of solid line. Okay, but suppose that the doping concentration is very close to the silicon atomic density. Suppose that, about, 50% of silicon atomic density, that is approximately 2.5 times 10 to the 22 per cubic centimeter. Maybe out of 5 times 10 to the 22 silicon atoms, half of it is non-silicon. Then we can say that, oh, I guess a two-third is silicon and the other one-third is non-silicon impurity. Then if we draw the energy band diagram for that material, maybe the dotted line, maybe the empty spacing between two dotted line would be, filled with the other, the other donors. So in the end, this dotted line would become a solid line like. So the original conduction band edge is E sub C here in. However, the rear or working effective conduction band edge would be very close to the or match to the donor's energy level. So this EC minus ED, what was it? Ionization ionization energy of dopant atoms, right? So a few tens of milli electron volts, say that 50 milli electron volts. This number has been lost when we estimating the band gap energy. So take a look at the scale of the y-axis here, 50, 100, 150 milli electron volt. Okay, so simply you can simply understand that once the doping concentration is super high, then E sub D, the donor's energy state, would be effective as or play a effective role as conduction band edge instead of the original conduction band edge. Okay, so you may simply and intuitively figure out how come the donor's energy state become an effective conduction band edge when the silicon material is very heavily doped. In other words, if dopant concentration is a significant fraction of the silicon atomic density. Okay, all right, that's all for the chapter 2. And please read all the sentences in chapter 2 of the textbook and do your best to solve all the example problem sets in the textbook. I guess that would be very good candidates uh, as a problem sets of your final exam as well as midterm exam. As of today, April 6th, I I'm not 100% sure we can meet together and take a midterm exam. However, I have asked headquarters of this university to have a on-site midterm exam in campus. I'm not 100% sure if we can do that, but let's see. Okay, so be prepared and be ready to take a midterm exam on April 28th, Tuesday, in class from noon to 3 p.m. Okay, so don't forget it. And I have already officially posted the midterm exam date, April 28th, Tuesday. Okay, whatever the type of midterm exam is, we're gonna take it on that date. Again, April 28th, Tuesday, the last Tuesday of this month, April. Okay, so that's all for chapter 2, and I'm going to collect a few problem sets to train you. So I'm going to post the problem sets in iCampus. Please download it and solve it just for your preparation of midterm exam as well as final exam. Okay. Okay. Uh, Let me stop here because I would like to start chapter 3 in a new movie clip file. So see you in the other movie clip.